Okay, class. So let's start. Got some error as well. Sorry. Okay, so I think I show you the the peer-to-peer program. Quite helpful for those who got you need help for physics. Okay, so you'll be paired with good students. Normally they are good in physics. Normally, okay. So to get some sort of a help. Okay, so please what? Today is the last day. So please enroll those less than need help for physics. Okay, and this program cannot be. It won't work if those who are good in physics, like more than 80% for your SEM1. Also, please, we need your help. Okay, we need you to be paired with the one need help. Okay, so please apply too. So you'll be getting certificate. Those who get more than 80 to help your friends. Okay, so apply by today, 2023. I think I put the information in the WhatsApp, right? Last week. Okay. Okay, so let's see. Go ahead with this topic. This is the fifth topic about thermal. I told you that. Okay, yesterday just introduced with the specific capacity latent, which you learned before. It's familiar, right? So, okay, let's see. Recap again. So, specific capacity is, of course, the amount of heat energy required to rise 1 kilogram of substance by 1 Kelvin. So, joule per kg per Kelvin, right? So, a good conductor has a very low specific heat capacity, and not a good heat conductor will have a very high specific heat capacity. Why water used as a radiator substance for the car engine? Because it has a huge specific capacity or low specific capacity. Because there's a huge specific capacity, so it can absorb lots of heat, but still the temperature never rises. Okay. So yeah, so Q equals mc theta. So what is Q? Mc theta all represents Q is heat energy, M is the mass of the substance, C is the specific capacity, and theta is what? Temperature change. Okay, write it, recall back. Okay. So now something new has been introduced, heat capacity, C. So what is capacity? Heat capacity is without per kg, without per kg, joule per, what do you call? Joule per kilogram. Okay. So the unit for, of course, unit is joule per Kelvin, joule per Kelvin for the heat capacity, big C. Okay, actually, as I told you, heat capacity and specific capacity is related like this, right? Mass times specific capacity, so heat capacity. Okay. For example, aluminium. A small plate of aluminium or big plate of aluminium. Aluminium has the same specific heat capacity, but heat capacity can be different. A kettle made of aluminium, another substance which is quite big than kettle made of aluminium. Both of them have a different heat capacity. Capacity dependent mass. Okay, the first one. Okay, give a try. Come on, just warm up question. So an aluminium electric kettle of mass 1.5 kg when empty. The specific heat capacity for the aluminium is 900. Determine the heat capacity of the empty kettle. Okay. Warm up questions. Okay. Determine the heat capacity. So heat capacity is mass times specific heat capacity, right? So 1.5 multiplied by 900, right? So you get how much? Get the answer, 1.5. So how much? 1350. 1350 joule per Kelvin, right? So heat capacity. Okay. Okay, let's be move on. So next one. Okay, next, specific heat capacity of water is 4,200. Determine the heat capacity of 2 kilogram of water. So heat capacity is what? The mass times the specific capacity for the water. Okay. In this case, 2 times 4,200. 8,400 joule per Kelvin. Heat capacity. Okay. Okay. So a new quantity has been introduced, like heat capacity. Okay, next. If the aluminum electric kettle is filled with 2 kilograms of water and the temperature of the water and kettle is rise from 20 to 100 degrees Celsius, what is the amount of energy required? Comment your answer. Okay, so energy, of course, both energy add up, right? Kettle absorbs heat energy, the water also absorbs heat energy. Of course, you thought of MC theta. You can check, you can use MC theta if you want. But here, heat capacity, we make use of heat capacity. Heat capacity of the kettle times the temperature difference of the what? Of the kettle, okay, plus C changes of theta of the water. Also can be used to find the energy, right? Heat capacity times changes in temperature will give you the energy. Yeah. So above for the water, 8,400 times 2, of course. And the kettle just now, what you got? 1,350, right? 1,350 times, sorry, this is 8,400 times 80, yeah? Not, it should be 80, right? Temperature difference is 80. And heat capacity for the kettle is 1,350, right? Yeah, earlier, 1,350. So for the kettle is the heat capacity 1,350. Temperature change is how much? 80. So you get the answer. Joule. So you get the answer. Because sometimes in the exam question, they don't give specific capacity, they'll give you heat capacity. So don't go and look for mass. Heat capacity, the mass is already multiplied into the specific heat capacity. Okay. Look at the energy. Okay, so this is just warm up, not that difficult. I'll come back to the experiment later. Okay, now a little challenging one. You get to know MC theta ML since 2 years back, right? Since you're Form 4, Form 5 for SPM and O levels. Okay, use your knowledge. You will try a little challenging one. Okay. Steady stream of air is drawn through a tube which contains 500 watt heater. Given that the density of air is 1.2 kg per meter cube, and its specific heat capacity is 1,000. Calculate the maximum temperature rise of the air for a flow rate of 0.4 meter cube per second. Okay, this is really a little tricky one. Okay, give you 2 minutes, come on. Try to work out. The example 2 is like same like an air dryer, You have an air dryer, okay. The air dryer, of course, the air was get into the dryer. The air dryer has its own heater inside. It heats the air. When it comes out, the air becomes hot. So this is the initial temperature. Of course, this is the final temperature. How hot the air comes out depends the power of the heater inside, right? And how fast the air is moving in the dryer. How speed? You put slow speed heater, the hotness very high. The temperature very hot. When you put a high speed, the air, not enough time for it to get hot. Yeah. So this is analog to an heater. The air in the heater was moving with 0.4 meter cube of volume of air is traveling inside the tube. You know what I want? Calculate the maximum temperature rise. How much temperature rise? Maximum temperature rise. That means theta F minus theta I. What is the temperature differences? 2 minutes for you. Come on. I want the answer from you. How many degrees Celsius? Or you can say how many Kelvin? You can have discussion with your friends if you want any input. So you must make an equation. Something equals to something to start with. The energy released by the heater equals to the energy absorbed by the water of the air, right? Right. The energy given out by the heater is equals to energy absorbed by the air. So from there you have to work up. Come on. How much energy given out by the heater? What formula do you use? Energy released by the heater. The power of the heater is 500 watts. So of course, the energy absorbed by the air, of course, what type of energy it absorbs? Heat energy, right? Okay. The energy released by the heater is actually the heat energy of the air. Okay. Heat absorbed by the air, right? So heat energy, what formula do you use? MC theta ml. No point ml here, right? No phase change. It's just air, still air. So it's only MC theta, right? So energy released by the heater is equals to heat energy of the air, MC theta. Come on, 2 minutes. I want the answer from you. Anybody? What is the temperature difference? Give me 2 minutes. Try to figure out. Okay, so first line I write to help you out. Energy release, released by heater, right? It's equals to energy, heat energy of water, of air. Yeah. Finally, you need to get what is the temperature change. Energy released by heater, what formula do you use? Energy released by heater. Power given 500 watts. So, what formula? Anybody? Energy released by heater. Power times what? Power times time, right? So PT. Energy released by heater is power times time. We don't know the time, okay, but we have to use power times time, no choice. Energy of the air, heat energy, MC, changes of theta. Okay, come on, guys. Look up. Let me give you the second line. Find the changes in theta. It's not a direct question, because mass not provided. Mass of the air is not provided, but density of the air given, the rate of flow given. Can you change the mass in form of density and Rate of flow. Figure out 2 minutes for you. So bring in density first, right? So mass we convert to density. How do you convert mass to density? So density times volume, right? So the next line is what? Pt equals to the mass not given, but density is given. So we have to convert mass to density. So density times volume, C changes of theta. Okay, next line, right? Density times volume. Okay. But you know 0.4 meter cube per second is actually what? It's actually what value? Volume per unit time. Right? It's actually volume per unit time. I think we can solve, right? So let me go and write here, no space. So P equals to rho V over T I pack together C changes of theta. Okay, right. Now you have all the values, right? Power is what? Power is 500 watts. Density is what? 1.2. Volume per unit time travel in this instrument is what? 0.4. C is what? C is what? 1000. So you find the changes in temperature. So you get changes in temperature. Okay. So 500 divided by 1.2, 0.4 times 1000 your answer for changes in temperature. Anyone? What do you get? The changes in temperature is what? 500 divided by 1.2 times 0.4 times 1000 at the bottom. If you change in temperature in Kelvin, right? Because the unit for specific capacity is per Kelvin. Okay, anybody got the answer? How many Kelvin you got? 500 over 1.2 times 0.4 times 1000 at the bottom. Okay, so hope you got the answer. Okay, important is the working. So whenever they give mass in the equation, but density is given, so I have to, of course, the mass convert to density times volume. Then you try to work out. Okay, so yeah, that's the question. Okay, this question is not that tricky. This I feel is okay, manageable. Should be able to do. Give a try this later. Okay. Okay, now that day also we learned about specific latent heat, right? Latent heat of vaporization, latent heat of fusion. Okay. So when the solid heated, its temperature rises due to increase of the internal energy of the solid. We will come back what is meant by internal energy. Okay. So whenever heat supplied, the internal energy of the substance rises. Okay. So straight go to the latent heat first. So latent heat must be supplied when change from phase change, right? Solid to liquid, liquid to vapor, liquid to solid to vapor. So specific latent heat of fusion is what symbol? Of course, is we put as LF, and the vaporization is L. LV. LV. What is the unit for latent heat of fusion and vaporization? Joule per kg, right? Joule per kg is latent heat of vaporization and fusion. Okay, for any substance, fusion greater or vaporization greater? Last class we discussed that, right? Vaporization always greater than fusion. Why? Because vaporization, you must do work to expand for the expansion. Work need to be done again as atmospheric pressure during expansion. Okay, on top of breaking the bond. Fusion energy is just used to break the bond, but vaporization energy is used not only to break the bond, but work need to be done against atmospheric pressure during expansion. During expansion. Actually, as I told you, lots of energy is used to do work, about 4 times greater than the energy used to break the bond. Okay. Okay, so the formula is ml, right? Okay, based on that, can we answer for this? Example 4, work up ml, latent heat of fusion, latent heat of vaporization. 2 minutes for you, calculate. Okay, so be careful there, a little tricky. With answer. Calculate the rate of transfer of heat. Rate of transfer of heat is actually power. Power, they're asking for power. How many watts? 2 minutes for you. This involves specific heat capacity and also latent heat, right? Both involved. Because 5 minutes 30 seconds is the duration it took to what? To freeze the water. To freeze the water. To freeze the water. So the water at the beginning was 20 degrees Celsius. So 20 degrees Celsius is going to drop to 0 first without phase change. So MC theta need to be used to calculate that energy. 20 degrees Celsius drop to 0. Okay. Then for freezing, you must use ml, latent heat, right? And the total energy divided by the time will give you the rate of transfer of heat, right? Come on, get me the answer. Calculate. So they are looking for power. First of all, you should know power. Total energy transferred over the time taken. Total energy transferred because the water, right? The temperature was dropped from 20, dropped to 0 first. Okay, dropped to 0. Then it was freezed. Okay. So this one is MC theta, and this should be the ml, right? So the energy absorbed is actually MC changes of theta plus ml over the time taken, right? So yeah, this is your idea. So those relays should be MC theta and ML to be used. Good. So MC theta, M is what? M is of course 0.5. C is what? Heat capacity 4200 for the water, specific capacity. Temperature change is how much for the water? 20 drop to 0, right? So temperature is 20, right? 20 plus latent heat of fusion 0.5, the mass. Latent heat of fusion is how much? 3.36 times 10 to the power of 5. Yeah, this the total energy has been removed from the liquid. Time it took is 5 minutes 30 seconds. So change to second, right? 5 minutes 3,000, how much? 330 seconds, right? 330 seconds. Okay, good. So yeah, whatever you got here, that's your power. Power. The rate of heat has been transferred from the liquid. Okay. Okay, those who thought of these ideas, good. MC theta plus ML. Best way, what you can do, whether to check whether got MC theta ML, what are the things involved? Draw the temperature versus time graph for that substance. Draw the temperature versus time graph first. When the temperature change go down, MC theta involved. Flat line, ML involved. Okay. Sometimes without drawing graph, we forgot there is MC theta. Okay. So draw the graph like theta versus time. Okay. Okay, so hope you got the answer. Important is the technical as usual. MC theta plus ML. Okay. Okay, so now let's go to the another one. Okay, this is also a little challenging. This I want the answer from you. Okay, no input from me. Give a try. 2 minutes. Let me get the answers from you. No input from me for this one yet, but I want the answers first. So see who can get the answer. Must make an equation. Something equals to something. Okay. What equals to what? To get this ratio. Okay, to be added, you can visualize like for this to happen, they use the same freezer, same freezer which has the same power, same freezer. Okay. To drop the temperature at the same time to freeze the temperature, done by the same freezer which has same power. Okay. You can discuss if you can share your ideas, but I want the answer. Give 3 significant figures. The ratio going to be more than 1 or less than 1 without calculating. Without calculating, it's going to be more than 1 or less than 1. Heat capacity greater or latent heat greater? Maybe your whole ideas. Heat capacity greater or latent heat greater? When energy is a lot, to rise the temperature by 1 degree Celsius, you need lots of energy, or to change phase, you need lots of energy. To change phase, right? To change phase, you need lots of energy. So the ratio going to be less than 1 or more than 1? Definitely going to be less than 1. Tell me 3 yes, sir. 2 minutes. If you got wrong, it's fine. Just give a try. Just give me the answer. What is same with what to start your working? What same with what? Something same for these two process, right? What same? The power, right? The power of the freezer is same, right? The energy has been removed from the liquid with the same rate, because same freezer, same freezer. During reduction in the temperature, the heat energy removed from the liquid with the same rate during the changing phase 2. So power same. The power of removing the energy. Okay. Power during temperature decrease is equals to power during freezing. So that's the first line. It's the same freezer. The freezer take out the heat energy with the same rate. Okay. So from there you can work out the ratio already. Anybody got answer? Give a try. Fractions less than 1. Now, because of online class, we facing a big problem. Although face to face, still all are just WhatsApping dances. Okay. New problem with the new generation. Okay. All because of COVID. So yeah, hopefully change. Anybody? Francis? Questions? Yeah. 140. 1 over 40. 1 over 40, yeah? 1 over 40. Let's check. If you got 1 over 40. So many saying 1 over 40, yeah? Okay, so how do you start your working with? The power to reduce the temperature. The power should be the same. That means power mc changes of theta over time should be equals to ml over time. Okay. Time taken during reduction in the temperature is the same as time taken during, the power during freezing. Okay. The time is not same. This T1, T2, the duration is, of course, is different. Okay. Okay, so let's see, work out from here. We are looking from here, you have to adjust so that until towards the end you get what? C over L is what? Yeah, you need to get C over L, right? Okay, can we start working from here? So M is what? Mass. Mass, is it the same? Yeah, same mass, right? Both of them same mass, right? The water is the one freezed. So mass we can cancel. cancel the mass. So C, we are looking for the ratio C, leave it. But changes of theta over T, we know the value, right? Changes of theta over T is 2 degrees Celsius per minute. This is your theta over T, right? Changes in theta over T, right? Okay. So L, we don't know. We leave it as L because we want the fraction. So L. Time for freezing is how much? 20 minutes, right? The temperature then remains steady for 20 minutes. Steady means it's freezing, right? The duration of freezing. So ml is actually 20 minutes. So the time here is actually 20 minutes. I can put 20 times 60, change to seconds. Yeah. Correct. Yeah. C. Here is 2 degree per minute. So per minute. I think here no need to change to minute. Just leave it as 20. Yeah. So because the other side also per minute. So I just leave it as 2. 2 per minute. L. So over 20. Correct. Yeah, very good. So C over L, you get what? Of course, 1 over 40. Very good. So C over L is 1 over 40. Good. Specific capacity is 40 times smaller than the latent heat of a substance. Latent heat energy is a lot, not very little, a lot compared to specific capacity. Vaporization even bigger than fusion by 4 times at least. Okay, class. So that's all for today. So start late. So tomorrow we will be continuing with the internal energy, something new. Okay, thanks.